Welcome to today's webinar. The topic today is the most common user errors with RFEM and RSTAB. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal Software company. For instance, the website, press releases, and the German and English webinars, etc. I will be the presenter today. My colleagues Markus Baumgartel and Stefan Frenze will support me. They will answer your questions. How you can ask questions. Let me at first switch off the camera that you can see the whole screen. Okay. On the right side of your screen, you can open a control panel where you can ask questions via chat. Stefan and Markus will answer you. If you don't get an answer during the webinar, because there are too many, you will get an email after the webinar. Here you can enter the question. So the other way is to watch the entire webinar and then email your question to info@dlubal.com. To the content today, I will introduce frequent input errors and explain how to correct them. And I will give tips and tricks for the application, for example, the FE mesh size, handling singularities, and correcting instabilities, etc. To the first task, we often receive models or model files from customers for which not enough wind load cases have been created for dual pitch roofs. According to Eurocode, there are at least 4 wind load cases necessary for the wind direction 0 degree and 1 load case for the wind direction 90 degrees. In the case, it's a symmetrical model. In our example today, we handle only this wind load cases because it's a symmetrical steel hull. Let's take a look at the first wind load case. There's pressure on the windward side, means the direction from which the wind is coming, and the leeward side, the direction downwind. Then here in the second picture, suction on both sides, suction and pressure, pressure and suction. Those 4 wind load cases are necessary. And for the wind direction 90 degrees, only suction on the roof. Let's turn to the program. That's the example that belongs to the PowerPoint slide. I created a load case, self-weight, and then the first wind load case. It's an automatically generated wind load. How you can do that for customers or users that doesn't know where you can find it. Under Tools, Generate Loads, there are a lot of load generators, for example, for snow loads, and here for wind loads on vertical walls, flat roofs, monopitch roofs, dual pitch roofs, and for vertical walls with roof. And I use this option here. Okay, let's open the wind load. That's the generator. Here you can choose the national annex, the terrain category, structure high, and then you need to define the base geometry by clicking 4 nodes and the roof type and geometry here by clicking 6 nodes. And this area here is for the wind direction. In this case, I used the A B wind direction means, for our example, the wind direction 0 degree. Okay, and this area here is important for the roof or the load on the roof. Those are the 4 wind load cases that are necessary according to Eurocode: wind plus, wind minus, minus plus, and plus minus. Okay, I leave the dialog and switch to this view. You can see 4 wind load cases for the wind direction 0 degrees are created. First wind load case is with pressure on both sides, then suction on both sides, suction and pressure and suction. Okay, then we turn to the next load case for the wind direction 90 degrees. I open it. Yeah, the upper values are the same, but the wind direction is now BCD. As you can see in the picture, it is 90 degrees. And I created, in this case here, 2 wind load cases, pressure and suction. And important according to Eurocode is the wind load case number 7 with the suction. Let's take a look again on the graphic here in the PowerPoint. That is the wind load case with the suction for wind direction 90 degrees. Okay. And then 2 load cases are created for wind in direction 90 degrees. The load case number 6 with pressure has no loads in the roof, because there is no pressure for the wind load case 90 degrees, but for the suction, there are suction loads. Yeah, load case number 6, this load case here does not contain any pressing with wind loads. Can be possible to or can be possible included to consider that the suction from the roof acts as supporting, but that depends on you. Important according to Eurocode is this wind load case here. Okay, that's all to the wind loads. I turn to the next task, imperfections. I create a new load case, imperfection towards plus x. Okay, and I would like to create imperfections for the outer columns on this side and on this side. I turn to the views navigator and use the visibility mode for beams. Okay, so then I open here above, insert, loads, imperfections, dialog box. So I don't care of these values here. Important for me today is this area here, members, list of members, sets of members. Okay, I select the members. Okay. Okay. So, and now I use the wireframe model. The imperfections are created but wrong, because the column is divided by a node because of the load in the load case number 1. Here's a load on the support from a console, etc. And therefore the member is divided. And that causes that the imperfection is wrong. How to create it correctly, I will show you. So I insert loads, imperfections, and I use the function list of members. Okay. The disadvantage is that I can only use one column because I can use the list of members only for members that are connected. Let me show you what happens. Okay, now the imperfection is created correctly. So, but I can copy that imperfection easily 3 times from this node to this node. Okay. Another option would be to copy that by selecting all imperfections and then using the CLRT key and then copy that via drag and drop. Those are right imperfections for the outer columns. But I would like to show you another option, in my eyes, better option. I create firstly sets of members. I select all the members and then open via right click the context menu, member, and then create set of members. Okay. 8 sets of members are created now. So, and then insert again, loads, imperfections, dialog box. And now I use the function sets of members here. And I can select all. Okay. And now the imperfections are correct as well. So that's all to the imperfections, how to create them correctly. And the sets of members in this case are useful anyway. I will describe you why. It's not only for steel structures, but also for timber structures, concrete structures. If a member, like for example, such a column is divided by a node, you need to define the the set of member, or you need to adjust the buckling length. What I mean, I will describe you now. I go in the add-on module of steel EC3. I select only this column here. Okay. Go into details settings and use here for the stability design the equivalent member method. I need to select one load case that I can come in this dialogues here. And by the dialog effective lengths members, you can see there are 2 members with incorrect lengths. The column has a length of 3.5 meters. And in this case, we would design 2 members with this one with a buckling length of 2.5 meters and this one for 1 meter. How to do it correctly? We delete the member or the members and select the set of member. Okay. And now the on module uses the right buckling length of 3.5 meters. It's quite important and a mistake that users sometimes or often do. Okay, that's all to this model. Let's turn to the next model. Contact solids. A lot of users have got problems with contact solids. It's a very valuable function, the contact solid, to define contact conditions between two surfaces. At first, I turn back to the PowerPoint slide. Solid type contact, the conditions. Parallel modeling is required for both contact surfaces, as you can see in this picture. Only exactly 4 lines are allowed for perpendicular boundary surfaces. This one is correct, and this one is not correct. The line and the nodes are too much here. And identical contact surfaces are necessary, including integrated objects such as nodes or lines. What I mean with that point, I will show you now. So that's a steel plate with a thickness of 20 millimeters. And here are stiff surface support. Could be that the plate lies on concrete, etc. And now I would like to copy that plate, and the other plate should lie on this plate. 2 steel plates and one directly over the other plate. Okay, usual workflow is to copy that plate. Okay, 1 times minus 2 centimeters. And then here I open the dialog and I create a solid between the surfaces. Okay. Okay. And now the column base plate is created and a solid between the 2 plates. Okay. Let's model the column. At first, I create a node between 2 points. Here in the middle, 50% and that point. Okay. And then I use the same function, copy, or similar function, -1 meter. And I don't create a solid, but a member. Okay. So I choose HEA 200 from steel S235. Okay. Okay. It is created, but it is still a member. And by right click, I create surfaces using the function generate surfaces from member. Okay, now those are surfaces. Okay, then I change the solid to a contact solid by double click. I change the solid type to the type contact, and there's a new dialog here, contact, and I can define the contact conditions. I select the first surface, the lower plate. Okay, it is the original surface, and the opposite surface is detected automatically from the program. That's the upper plate here. Then the contact conditions perpendicular to the surfaces failure under tension, and I define here parallel to the surfaces a rigid friction 0.2. Okay, and now I create or generate the FE mesh and get the message, error message. Numbers of integrated objects in contact surfaces do not correspond. Yeah, and that's correct. There are lines and nodes in the upper surface, but not in the lower surface. How we can handle this? I go again in the solid and I select the upper plate as original, and then the integrated elements are copied internally to the opposite surface, in that case the lower surface, and then the FE mesh will be generated. Let's try it. Calculate. Yeah, now it's correct. And as you can see in the upper plate, there is a disorder in the FE mesh because of the node here. Let's take a look at the lower plate, and here you can see the same disorder because there is an internal node copied from the upper surface, and that's why the FE mesh is the same for both plates, and now it is correct. Another way to define the solid, I will show you now the other way. Okay, I delete the solid and then I select both plates, and then by right click I select the feature create solid with contact. Okay, and now you can see the lines and nodes are copied not only internally, but copied right to the lower surface. And that causes that both plates have got the same integrated objects. So now at first I define the right contact conditions, failure under tension, again the friction, okay, and I generate the FE mesh. Next error message. That's a FE mesh problem. The lower plate don't need the lines and nodes. There are no surfaces or members connected to these lines, and therefore the FE mesh generator don't take care of disintegrated objects here. I need to open the FE mesh settings and select here integrate unutilized objects into surfaces. That's important in this case. Okay, and now we can generate the FE mesh. Now it's okay. The first option that I showed is the favorite in this case here, but sometimes you can only use the second option, this option here. I show you an example. That's a single span beam. Here are members, and here's the member divided into surfaces. And here in the middle are two plates, a solid between the plates, and also boards, all is defined. I need to define the contact solid, but let me show you what's the special here. Those lines here, or those surfaces, are from a IPE 160 and here IPE 180. And that's the reason why the integrated objects are not the same for both plates. And therefore, I can use only the option, or let me show you what not work. So contact, so failure under tension, rigid friction, a very small friction factor in that case, that the bolts get the whole shear force. Okay. So and then calculate, generate FE mesh. Yeah, that's the error message. Okay, let's try the other option. Okay. So I select the both plates here and create solid with contact. So, and now the lines and nodes are copied from the right side to the left and from the left side to the right. Okay, I define the contact solid again. So, and now I don't need to forget to change the FE mesh settings, integrate unutilized objects, and then I can generate the FE mesh. Okay, that works. Okay, I hope these tips could help for the solids, or especially the contact solids. Then we turn to the next example, FE mesh. We often get the question, what's the right FE mesh size is. Yeah, there's no general answer. It depends on the model. But what we can say is that we can refine the FE mesh until results do no more change significantly. You can see here a very fine FE mesh. Disadvantage of such a fine FE mesh is the long calculation time. At least if you have got complicated models, you often calculate models that are not so easy like this one here. Okay, let's turn back in the display navigator. The other option here, constant in elements. You can see here very large FE mesh, very large FE mesh size, 150 centimeters. Also, this FE mesh size is quite large, 50 centimeters. It's in my eyes okay, and the favorite in that case here. And you can see here the results are comparable. And if I switch to continuous within surfaces, I smooth the results more. You can see also for this large FE mesh size, the results are quite okay. But this one I think is better. Let's compare the results for this 4 slabs. By the way, the slab has a thickness of 200 millimeters and it spans for 6 meters. So I define a nodal support. At first I create a node between 2 points, as I did it before. Okay, in the middle. Okay, and now a nodal support. Only in Z direction. Okay. So then I copy it 3 times. Okay, then we calculate our new. So, and here you can see that there's a singularity. But I recommended to use FE refinements for FE mesh sizes that are larger, but okay. Let's do it. New FE mesh refinement. Rectangular on the nodes. This one, and this one. I don't need it here because the FE mesh is already 10 centimeters. Okay. Size length is 20 centimeters and the inner length 10 centimeters. Okay. Okay. So then we calculate our new. And now you can also see for the other slabs that here is a singularity because the nodal support has not only dimensions, for example, dimensions of the column, it's only a point, a peak, and that's why there is a singularity. How to handle this? We can smooth the internal forces with an average region. I create an average region now. Okay. The first on this point. Okay, dimensions. In this example, I use 40 centimeters. This could be the dimension of the column. And I smooth, or I would like to smooth the internal forces in all directions. Yeah. And I select all surfaces, or all 4 surfaces, to be able to copy it from this point here to the other surfaces. Okay. I use the function drag and drop by using the CART key. Oh, that was not so good. So that's correct now. Yeah, now you can see for all 4 plates, the results are smoothed with an average region. The results are quite similar for the field and over the column. Okay, that's all to this example. Maybe not another hint. You can define here not a stiff support to consider the elasticity of the support with this feature here, elastic support via column and set. And then you can define here the dimensions of the support or of the column, the material, height, etc. Okay, but I don't do it in this case here. Okay, that's all to this model. We turn to the next model, a very simple model, cantilever. So we can easily calculate the moment here, 10 kilonewton multiplied by 5 meters, 50 kilonewton meter. Shear force is exactly 10 and the normal force is 0. So, but when I switch to the load combination with only load case number 1, where the small normal force. It often happens that you get internal forces which you haven't expected, and that's a good example here to describe it. And in this case, it might be due to the fact that the internal forces have been referenced to the deformed structure. Let's turn, and you can also see here the shear forces are not exactly 10. So let's open the calculation parameters, load combinations. And for load combinations, the calculation is performed by default according to the second order analysis, and the internal forces are referenced to the deformed structure. Yeah, as you can see here. In my eyes, this is close to the reality when you have small deformations. In the case of large deformations, for example, tensile membrane structures, you should use the large deformation analysis. Okay, but that's those are the settings for, or the default settings for load combinations. Okay, we can leave the dialog. I show you the deformed structure. And you can imagine if the load vector is on this point here, the point of the deformed structure, the angle between the load vector and the beam is not only is not 90 degrees. And that's why there is a small normal force, and also the shear force is not exactly 10 in this case. I think with this deformed structure here, you can imagine what's the reason for such internal forces that you wouldn't expect. Next model. And another cause for unexpected internal forces are, or can be eccentricities. You can see here two frames. The left frame has no eccentricity, but the right one, here, the horizontal beam has an eccentricity. Yeah, and that's why we get the offset in the internal forces here. That's the my internal forces. Yeah, here's no offset without eccentricity, but here, because of the normal force in the horizontal beam and the eccentricity, there's an offset. Yeah, you should consider where eccentricities are useful and necessary. Respectively, you should consider here that offsets occur. So, yeah, for such models, or if you would like to create a composite beam or a plate over a beam with a loose or elastic support, then you need to define an eccentricity. Let's copy that model here. Okay, one time, 6 meters in X direction. And now I create an eccentricity. Okay, options. And here I can define member eccentricity. I use the function relative offset. The upper side of the beam should be on the lower side of the surface. Number 2. Okay. Okay. So now where's the right eccentricity? Can calculate all to compare the results. So the My internal forces, we can compare it for the beam, about 90 kilonewton meter, and here about 40 kilonewton meter. Now it's an eccentricity and a rigid connection between the beam and the slab. You can use it also for other materials, for example, timber beam and a timber slab or a CLT slab, but then you need to define an elastic support or a loose support. If you want to do that, you need to use the function align release. So we copy that model again, one times. Okay. So before I define the line release, I switch on in the display navigator here under model lines, the line axis system, that you can see how I define the direction of the nonlinearity. At first, I would like to define a loose support. So that's the line axis system. The plus Z axis is downwards. So, okay, and now I define the line release. Here, new line release. So at first I select the line. Okay, and here I define the line release type. So I define a small spring constant here to avoid the entire displacement of the plate in X direction. And here the loose support. And then I consider the nonlinearity fixed if positive Y set. So means that in Z direction, in the case of loading in the direction of the positive Z axis of the line axis system, the connection is fixed. In the opposite direction, it is loose. Okay. Then I need to define the released object, the surface, this one. Okay. Okay. So now I calculate R again. So let's compare the results. 90 kilonewton meter, where the beam and the slab has the same center of gravity. Then the composite beam, about 40 kilonewton meters, and here about 89 kilonewton meters. Similar to the first model, here we have got a loose support. So let's check if the nonlinearity is defined correctly. I change the load to -10. Okay. And calculate it. Yeah, now you can see a very large displacement. We can cancel the calculation. The plate would be lifted. Okay. So that's the proof that we defined the line release type correctly. Okay. So, and yeah, to consider elastic fasteners, we need to define a spring in X direction. Yeah, in that case, for example, bolts, or yeah, imagine you've got a timber beam and a CLT slab, and there are screws in the connection. Then you can define here in the release type, yeah, spring constant for the fasteners. Okay. Okay. So then let's compare the results again. So 90 kilonewton meters, 40 kilonewton meters, approximately at least, and about 70 kilonewton meters. Okay, yeah, you can define loose support or elastic support or a rigid support. Yeah, and how to do that, I showed you in this example. Okay, to the next example. A timber example. I open the general data. That's the first dialog when you create a new model. And a lot of customers forgot to consider the serviceability limit state combinations for timber structures when they use the automatic load combinations. Here they select this, but it's necessary to select this one here with the consideration of the Eurocode 5. And here you can define the national annex, and you can edit the parameters. Oh, and in this dialog, you can define the consequence classes and, here important, the service classes. Yeah, service class 1 in this case, and here's 2 and 3. You can also define a user-defined k-def factor. Yeah, in this case we use this factor here for the service class 1. Yeah, what is to say, since the creeping parts for the serviceability limit state design are considered directly from the load combinatorics, you have to define the service class and thus the deformation factor, no matter which design module you are using. It's a little bit hidden, this factor, but it belongs to the combinatorics. Okay, and you can also find this in the load combinations dialog here, or load and load combinations dialog here on the combination expressions on the lower side here on the edge. Okay, and here you can define the k-def. Please don't forget to use the Eurocode 5. That during the automatic combinatorics, the serviceability limit state design or the factors are considered. Okay. Yes. In this model here, I would like to give another tip. If you would like to connect two slabs, like in this case here, with a line hinge, use only one line hinge, not two, when you connect two surfaces. Then it might be possible that you get problems in the calculation. If you've got three surfaces in one line, only two line hinges are created. You need to define one line hinge less than the number of connected surfaces. That's a good rule. And then you don't get problems during the calculation. Okay, another tip here. Not only for timber structures, for all structures, I open the calculation parameters. Customers often call the technical support and complain about too long computation times. And they accidentally switched on the iterative solver. This is usually no more necessary when using today's computers. Direct solver is it's usually the best choice. Okay. Then we turn to the next model. We come to the last part of the webinar, to the instabilities. A very simple structure. In Y direction, we've got bracings from as tension members, and in X direction frames. And if we calculate the self-weight load case, we get the error message, the system or the model is unstable. What's the reason? If you have got load cases only with loads in plus Z direction, for example, self-weight or snow, then it could be that you get such problems here. What's the reason? The node here is moving in plus Z direction, and that causes that the tension member gets pressure and fail. And all members fail, and then the model is unstable. How can we solve that? Here in the calculation parameters, there are two different options. The exceptional handling, at first failing members to be removed individually during successive iterations. Let's try it. Okay, now this tension members are failed, and this one are still there, and this one, and that's why the calculation is okay for this load case. If you have a load combination, for example, with self-weight and wind in y direction, the members here are reactivated. We don't lost for the whole time. Okay. Then the next option, assign reduced stiffness to failing members. Here the default setting is the reduction factor of stiffness of 1000. As a very small stiffness now in the tension members. Let's calculate it. Now it calculates, no failure, but a small disadvantage is if I go to the result diagram, you can see there are very small negative internal forces, pressure in such a tension member. You need to consider, if you document the results in the printout report, there are small pressure forces. Okay, another option is, if you would like to calculate the load case, is to define a very small horizontal load. So 0.1 kilonewton, this node, and then we can calculate it. Okay, calculates, and then the last option. So I define a pre-stress of the on the member on the bracings, on the tension members. Initial pre-stress 1 kilonewton in that case. Okay, and I can calculate it. So now we get results. Okay, we turn to the next model. Yeah, simple steel hull. It could be also another material, it doesn't matter. I show you the loads. I created pre-stress for the tension members here, for the bracings, and I would like to calculate all. Okay, I get the error message. System is unstable. What can be the reason? Imagine you've got the model from a CAD model, you imported it via an interface, for example, and there are maybe small modeling mistakes in the CAD model, or it was a transfer problem, and you need to search the problem, or you modeled it incorrectly. For example, members are not connected correctly. You can use, for example, here under tools, the model check. There are different options here for the model checks. For example, the identical nodes. Then you can search for identical nodes. You can define here another tolerance. And in this case, that's not a problem. But you can find such model errors with this feature. Let's try another feature. I use the add-on module of stability, and I use the feature here, determine eigenvector for unstable model, so that causes of instability can be checked graphically. Let's try it, calculate it. Let's take a look at the graphic. You can see this frame is moving in X direction. Maybe you can see it again. I defined here member and hinges, and that's incorrect. Yeah, it could be a transfer problem, or you modeled it incorrectly. So I corrected it now and can calculate it. So now it's correct. Then we turn to the last model for today. I would like to show you another option to find instability problems. So a steel platform, and I calculate R. So the load cases are okay, but the combinations are not okay. So how we can handle this, I will show you now. For example, you can go to the calculation parameters. Yeah, you can see here I use the exceptional handling. Yeah, that is okay. And now I go to the load combination number 1. That the program not calculated. Geometrical linear analysis, and I modify load factor 0.1, that only 10% of the load are considered. Okay. Now I calculate it again. Now the load combination calculates with the very small load, and the inner frame is moving in X direction. So let's search for the problem. I change the visibility mode. So yeah, as you can see here, the same mistake, hinges on the edges here. Let's correct it. Double click, and then I can say here, no member end releases, or member end hinges. Okay. So then I cancel the visibility mode. And what is very important, to reset the calculation parameters when you find or found the problem. So I select again the second order analysis and consider a loading factor 100%. Okay. And then I calculate R. So now it's corrected. Well, small deformations in that load case here. Now the model is corrected. Yeah, that's the end of the presentation in RFEM and RSTAB. I hope I gave you some valuable tips and tricks. Before I show you where you can find the recording and the recording in the next days, and already now the models and presentation slides, I would like to introduce our free online services, the GeoZone tool with snow, wind, and seismic zone maps, the page with the cross-section properties, where you can also define parameterized cross-sections and calculate its cross-section properties, the FRQs and knowledge base. There are a lot of very valuable articles. You can download models, not only the webinar models, for example, to get started or to become familiar with the program. Then the YouTube channel with the recorded webinars and a lot of valuable videos. Our web shop is with prices. If you are interested in prices of add-on modules or programs or standalone programs, you can download our trial licenses for free. For example, the programs RSTAB and RFEM with all add-on modules, the standalone programs, for example, R-Wind simulation, Craneway, Shapefin, FE buckling, etc. If you haven't already registered for our newsletters, you can register on our homepage, that you get information about the next webinars, trainings, news about our software, etc. So then let's turn to the homepage. In the next days, you will get an email with a link to the webinar page. That's today's webinar here. And in the next days, you will find the recording here. That's another webinar, not the latest, but it was on the end of the last year, stability design. But in the next days, you will find today's webinar here. Then you can already find the presentation slides here and the models to download. All models that I showed in the webinar. And here will also the recording be placed. Okay, then I would like to say thank you for your attention. Thanks to my colleagues for answering the questions. When you leave the webinar, there's a small survey. It takes not very much time to answer the short questions. It's quite important for our quality management. Just note that the worst score is 1 and the best score is 5. You can imagine 1 star is bad and 5 stars are good. Okay, that's all. If you have any questions, just write us an email to info@dlubal.com. I say thank you, have a nice day, and bye-bye.